Okay, so this next topic is on thermal expansion. Thermal expansion just simply says that when materials heat up, when they increase in temperature, uh, they they generally expand. We'll look at particularly at solids, although we'll look later at gases and how this occurs. Well, interestingly enough, though, with water, as we said, this is not a curve with water. That when ice heats up, it actually, and when it changes state, that it actually gets smaller. But when materials heat up, and we're not actually talking about phase changes here, they expand. You see thermal expansion accounted for in a lot of different ways. Like when you're walking on the sidewalk, you see expansion joints in the sidewalk. That's because just in the daily temperature changes of cement or concrete, it will expand. And so they put these, rubber joints or these spaces between the parts in the sidewalk so that when it does expand, that the cement doesn't crack. Similarly on bridges, like here, you have these expansion joints in the bridges. You can often feel them when you're driving over a large bridge, like one of the Mississippi River bridges, uh, that are there so that when these very large structures heat up just day to day from the highest to the lowest temperatures, they can expand many centimeters, 10, 20, 30 centimeters, which is enough to cause structural failure if you couldn't account for this expansion. So you have to include these expansion joints. You also get expansion that occurs in all dimensions and linear expansion, which is what we're going to do here, but you also get area expansion and volume expansion. So like if you have a three-dimensional object and it heats up, it's going to expand in all directions. But we won't deal with that here. We'll only deal with linear expansion, which is quite a bit simpler. Linear expansion, if we have a bar of a certain length, L naught is its initial length, and you heat it up by a certain temperature, then you experience a certain change in length. And we can calculate that here. Delta L, which is the change in length, is equal to something we call the coefficient of linear expansion, alpha. It's a quantity, it's just found experimentally. You heat up a material, you see how far it expands, what's its new length, and then you can calculate the coefficient of linear expansion from that. L naught is the original length, and delta T is the change in temperature for the object. Not its final temperature, but its change in temperature. Here's some coefficients of linear expansion for various materials. Notice that aluminum, for example, has a larger coefficient of linear expansion than steel or cement. I'll give you this table for future quizzes that you'll need it. Here's a clicker question for you to try out. I want to know, this is the period of a clock, and at a certain temperature, we want to know what is the new period, or this expression is used to find the period of a pendulum, and it tells you that it's 1 second at room temperature. The length of the rod is that amount. So what is the period at this new temperature, a much higher temperature of 320 degrees Celsius? So the length of this pendulum is actually going to get longer at this higher temperature, and it's going to change the period of the pendulum for the clock. I just tell this story about this wedding picture. We had this wedding picture, a picture that was given to us for a wedding. It was a crystal picture. It was glass, or it was crystal. Looked like that, I guess. And I have to make the tea in our house because my wife's from Missouri and I'm from Mississippi, and somehow she thinks that like she can't make sweet tea. She really just doesn't put enough sugar into it. But anyway, that's beside the point. I make the tea, and whenever I make tea, I always pour the hot tea into the container, put the sugar in, and then add cold water to make the iced tea. But when you do that, when you pour a hot liquid into a material like this, it actually causes the material to expand, but it doesn't cause the entire material to expand all at once. Let's see, I think I have a picture here. So here, if I put hot water in here, it causes this portion of the container to expand, while this portion doesn't expand at all. And that causes, of course, it to crack. So when you pour a hot liquid, a boiling liquid into a glass container, it can cause it to crack. Now, some materials, such that Pyrex, does not easily break, and that's because it has a much smaller coefficient of expansion than glass. Pyrex is glass that has been heat treated, so it's raised to very high temperatures and it's cool, and that makes this glass very heat resistant. And if we look back at our coefficients, let's see, where are they? I have Pyrex here. Yeah, see, Pyrex is 3.2 times 10 to the minus 6, and glass is 9 times 10 to the minus 6. So Pyrex only increases in length by a third of what glass increases, and that's why Pyrex is heat resistant. We also see this existed in or demonstrated in bimetallic strips. These are used in a number of different places where you want to find the temperature. Bimetallic strip, for example, this one is steel and brass, and if I heat this up, I want to know, does it bend up or down? So one of these is going to expand at a greater rate than the other, and that one that expands at the greater rate, it will bend away from that material. So I'll let y'all try this, but both of them are going to expand in length, but one of them will expand a little bit more because of its difference in the coefficient of linear expansion. So you can think about that and then answer this online. But this type of strip, this bimetallic strip, is sometimes used in thermostats because when the temperature changes, if this is my bimetallic strip, it's going to either coil up and get tighter or loosen up and get more loosely coiled, and that's going to cause your temperature dial to move in either direction, depending upon what the temperature is. So it's calibrated properly. Now, some of your old thermostats in home, some of you might have this in your home. If you take the cover off your thermostat, especially if it's not a digital thermostat, then it likely has this coil of wire in it, this flat bimetallic strip that changes its tightness or looseness of the coils depending upon the temperature. There's another quick test question. We'll pause there.